Okay. All right. So for starters, next week we have an exam. We have our second exam. Hi. Next week we have our second exam. It's non-cumulative, meaning it will not cover material that was present before exam one. Only material since exam one. So exam one, I think we covered pretty much. We covered data types, diagnostic tests, probability, Venn diagrams. We had a whole bunch of things that we covered before that. Towards the end of that period at exam one, we started covering confidence intervals. Okay, and in the crossover, we went from confidence intervals, we went into central limit theorem. Okay, which was the property of how samples act, numerical samples act. And we learned quite a bit about how we can apply that to confidence intervals, to comparing means of two populations, comparing means of three populations or more populations. And most recently, we've been learning about how to apply statistics to categorical variables, namely when you have two or more values for one category and two more values for another category. In other words, chi-square and odds ratio, for instance. Okay, so I'm going to try and do a basic kind of quick review of all those things, but that's the material that will be on the test. A little bit on confidence intervals, just, because it kind of really ties into this stuff. A bit on the central limit theorem, okay, as it ties into samples, t-tests, chi-square, and so on, analysis variance, and so on. So one of the things that you might consider doing is go back over the PowerPoints for the lecture sections that were the lecture recordings and so on and so forth, or the other material like that. And whenever you see a test like a t-test, chi-square, odds ratio, or something like that, take a look at those PowerPoints. And in those PowerPoints, you'll see some mention of what the rules are for applying that. In other words, what the assumptions are. So assumptions for the t-test may be that the original, if it's a small sample, the original population is roughly normal. It may be that it's a random sample. It may be that the two groups are independent, right? So there are three things that are things that are requirements for doing the t-test properly. When we get into chi-square, there might be issues about sample size, such as if we have a 2x2 table, we want to make sure each one of the boxes, especially the estimated, the expected values, has at least 5 subjects in it, number 5 in it, or larger. So we'll be, on the test, we'll be covering confidence intervals. We have charts on how to calculate. We have some tables and pages on how to calculate confidence intervals. As a reminder, we're going to go through them now as well. And then we moved on to numerical variables, where we wanted to compare, say, just 2 groups or one group to a new sample from another group. Okay, so we have various ways of doing that. They're all basically t-tests, where you compare two means, means for 2 groups. In one circumstance, the true mean for a population, and you're going to take a second population, take a sample, and compare the sample mean from that population to the known mean for the other population. That's called a single sample t-test. We'll do an example of that this afternoon. Then we have situations which are very common, even more common, where we're looking at 2 different groups. For instance, you guys, as I was talking to a student here, we might be interested in whether or not women who have HIV, if their babies are HIV positive or not HIV, based on some blood test. Okay, I'm gonna make up a parameter, vitamin D levels, for instance. So if the mother's vitamin D level average, we're going to take a look at the babies that were positive, of HIV positive, babies that were HIV negative from HIV positive mothers. And we're going to look to see if the average vitamin D level during the mother's pregnancy was higher or lower for infants who were born HIV positive versus HIV negative. So how would we do that? Well, we got two groups. They'd have to be independent. Obviously they're not the same mother. The baby, we wouldn't. Perhaps we would exclude twins or something like that. The result might not be independent. We would want random samples from each of the two groups. We want a random sample within the two groups, and it would help if we're going to work with a very small sample. We'd be a bit concerned about whether or not the original population, the vitamin D levels for the original populations were normal. As the sample size gets bigger and bigger and bigger, especially if it's a very large sample size, well, in that case, we might be far less concerned about whether it's a normal, the original populations have normal distributions in vitamin D levels. Because central limit theorem tells us as the sample gets larger and larger and larger, that we're less dependent on that being true. In other words, we can expect, as we get larger and larger samples, we can expect the distribution of sample means from a population to be normal, even though the original population might not be perfectly normal. Right. So that's a key about the central limit theorems. That might come up in a multiple choice question, for instance, right, or a matching question or something, right? So we would use a t-test to compare those two means. Okay, that's called an independent samples t-test. We have a sample from one group and a sample from another group, and we're comparing the two of them. Very often used in experimental studies. For instance, if you're giving one group a drug and another group a placebo, and you're controlling it, in other words, second group, placebo group is a control group. So you have an experimental group and a placebo group, and say you're measuring blood pressure or something like that. You can compare them directly, the average blood pressure of the two groups directly. So very often used in experimental groups. One little kind of tangent on that is whether or not the variability in your two groups is the same or not. So one circumstance that you might have is that the variability of blood pressures in one group may be much greater than the variability of the blood pressures in the other group, no matter which direction it is. Well, if the variability is just similar, right? We can combine those two groups to create a pooled standard deviation, which we can use to help us determine whether the samples from the two groups indicate the populations have significantly different means. In other words, reject our null hypothesis. If the variability in the two groups is very large, well, then we can't pool the standard deviations. We have to handle them slightly differently. So I'm going to remind you that there's a document that we have that describes how to do it in assuming equal variances, how to do it assuming unequal variances. I'll just bring that up to remind you of that. So we'll have, and there's still both. Whoops. I think I lost my connection here for a moment. You guys, can you see anything moving around there? Okay, good. So we'll have a circumstance where they're both independent samples t-tests. So we have single sample independent samples t-tests, assuming equal variances or not assuming equal variances, right? But both still independent samples t-tests. And then we have paired sample t-tests. And in paired sample t-tests, we might take 100 individuals. And if I went back to the idea of testing whether or not a placebo or a drug lowers blood pressure sufficient more than if a drug lowers blood pressure more than placebo does, the way we might handle that is instead of having two groups, one to whom we give the drug, the other that we don't give the drug, instead of that, we'll have one large group, and each individual, say there's 100 of them, each subject will get will be given a drug for 6 weeks and measure his blood pressure or decrease in blood pressure, and then he'll be switched over to the placebo for 6 weeks and measure his blood pressure then. And then with some of the individuals chosen randomly, some will get the placebo first, some will get it second, some will, and so on and so forth. And then at the end of all that, we would look, rather than look at the comparison of placebo versus a drug, since each person contributed data to this, we would just look at the difference for each subject between what their blood pressure was on the placebo and what their blood pressure was on the drug. And our expectation is that if the drug doesn't do anything, the difference would be 0, right? So then we would wind up with 100 subjects, their blood pressure before with the placebo or without the drug, each one of them with the placebo or with the drug, and we would find a difference. So we'd have a final column that has all the differences. And if we find the average of the differences, our expectation is if the null hypothesis is true, then the average of the differences should be 0. But if our null hypothesis is false, we would expect average differences to be not 0, to be different than 0. So in other words, mu for the differences is equal to 0 is our null hypothesis. Mu for the differences not equal to 0 is our alternative hypothesis. That effectively, that paired sample t-test is effectively a single sample t-test where you're comparing the results of the differences, average result of the difference, to the value 0, to the imaginary population that has 0 difference. And we'll get, again, this is a little less obvious when I'm just talking about it. When I write this stuff down or show it to you being done with SPSS, I think it'll make a bit more sense to you. Okay, so now that we've done that, we also have situations where we have more than 2 groups and we want to compare the means of more than 2 groups. For instance, if we wanted to compare placebo to 2 different levels of 2 different dosage rates of the drug, now we have 3 groups. We have group 1, drug group 1, drug group 2, drug group 3, and we want to compare the means of the blood pressures of the individuals in the study for each of those 3 groups, and they were randomly selected. So it's not a paired sample t-test anymore. It's 3 independent groups. Now, in that case, we're comparing the means of those 3 groups. So our null hypothesis would be mu1 for group 1 for the drug group 1 is equal to mu for drug group 2 is equal to mu for the placebo, assuming that there was no difference between the drug groups and the placebo, etc. So in that case, we have to compare 3 means. Well, let's say that there were 3 or 4 different dosage rates for that drug. Well, now we have 4 dosage rates for the drug plus the placebo group. So now we have 5 different means we have to compare. Mu1 is equal to mu2 is equal to mu3 is equal to mu4, and so on. So in that case, we could use a t-test, but we would have to compare, if we wanted to compare all those different means, we would have to compare the mean for the drug 1 to drug 2 to drug 3 to drug 4 and to placebo, and then drug 2 to drug 3 to, and so on and so forth. So we would be running that t-test 20 or 30 times for those groups. So that would introduce a lot of error, because each time, if we use a alpha of 0.05, we'd have a 5% risk of rejecting the null hypothesis for each of those different comparisons. So we need another way to do that, and that's where analysis of variance comes in. Analysis of variance allows us to compare the means of more than 2 groups all at once. If the analysis of variance, which is the F statistic, if that exceeds the critical value for the F statistic, for that number of for that number of groups, and for that number of people within the groups, then we can reject the null hypothesis, meaning that our alternative hypothesis is satisfied. It's a little unusual because our alternative hypothesis in that situation is that the means of the groups, of at least 2 of the groups, are different. Not all of the groups have to be different to reject the null hypothesis. In other words, mu1 equals mu2 equals mu3 mu4 is equal to mu5 is a suitable alternative, is a suitable null hypothesis. but mu1 does not equal mu2, does not equal mu3, does not equal mu4, etc., is not a suitable alternative hypothesis, because the alternative hypothesis is that at least two of the groups are different, have different means. So what do we do then? Well, if we fail to reject the null hypothesis, that means that we can't prove any of the groups are different. It means that any of the groups are different, so we're done. If we can reject the null hypothesis that all of the means are equal, right? Well, then we have to determine which ones are equal. So then we do additional tests called post hoc tests that allow us to examine each one of the comparisons, group 1 to 2, group 1 to 3, group 1 to 4, and so on and so forth, individually, to see which of those groups has a probability of a p-value, a significance of less than 0.05, so that we can say statistically that the means of those two groups are different, with at least less than 5% chance of inappropriately rejecting the null hypothesis. So that's analysis of variance. Then finally, chi-square, which I'll save a more elaborate description of for after we get through all this other stuff, because it's a bit different, because then we're talking about categorical variables. And in that case, we're looking for an exposure and an outcome that are in categorical form, such as both variables, instead of one variable being nominal, for instance, drug group or placebo group, in other words, which group they're in, is a categorical variable, and the actual blood pressure measurement is a numerical variable. Instead of that, we might have a situation where we might just be looking at drug versus placebo, and the other variable might be blood pressure, high or normal, right? So now it's categorical variable. It's high or normal, not a specific number, right? So in that case, we can create a contingency table, very similar to our diagnostic test, where we put the exposure, the drug or the placebo, in the rows, and we put the outcome, whether or not they have high blood pressure, in the columns, and compare the two of them. That also allows us, if it's a 2x2 table, we can calculate a chi-square value, and again, check it against what the critical value of chi-square would be for that for a 2x2 table, or indeed it could be a 3x2 table or a 3x4 table, and so on and so forth, and decide whether or not we can reject the null hypothesis. Null hypothesis being that there's no association between the two variables, blood pressure and the drug, whether or not they're taking the drug, and the alternative hypothesis being that there is an association. Whether taking the placebo or drug does make a difference in terms of whether or not they have high blood pressure or not. So that's where we work with how we work with chi-square. We also with categorical variables, if we're working with 2x2 dichotomous variables, where like the one I just described, each variable has two values, the exposure and the outcome have two values. In that case, we can also calculate a statistic called odds ratio and relative risk. And in that case, a relative risk or odds ratio, we're looking for an odds ratio or relative risk, where the risk of our null hypothesis is that the risk of having high blood pressure for the drug group is the same as the risk for the placebo group. So in other words, the risk would be the rate at which people that took the drug have high blood pressure, and the rate at which the percentage of people that took the placebo that have high blood pressure. So if it's 30% and 15%, our relative risk, or also called often our risk ratio, would be 30% over 15%, or a 2, which indicates that if you're not taking the drug, you're twice as likely to have high blood pressure. Your probability of having high blood pressure is twice as likely. Similarly, we can calculate odds ratio. Well, knowing that that's the way we're doing it, you can figure that if the likelihood is the same for having high blood pressure, whether you take the drug or the placebo, well, the percentages are going to be the same. So the percentage might be 25% for the drug, 25% for the placebo. So when you divide one into the other, it's going to be equal to 1. So hence our null hypothesis for relative risk or odds ratio is relative risk or odds ratio equal 1, and our alternative hypothesis is that relative risk or odds ratio is not equal to 1. Okay, so that's the last 6 weeks in a nutshell. I don't know, you guys are way too young to remember the Smothers Brothers show. It was on in the 60s. But they used to have, every couple of weeks, they used to do a thing to some music where they would do like American history in like 60 seconds. And they would flash a picture up, like every, some part of American history, starting with the Revolution, they'd flash a picture on the screen like every quarter of a second. So it was just above threshold. So you could actually see what it was, but it was gone like in an instant. And in a minute, you would see all of American history. This is what we just did now, right? Okay, except it had musical background, right? This didn't have musical background. Instead, just had my drone saying this. Hopefully now when I actually start to work on the screen, it'll make some more sense to us. But that's kind of in a nutshell where we've been and what we're up to at this stage. Okay, so these kind of variables. Now, and do you want to take a guess at what is the combination of variables that we haven't dealt with so far? We've dealt with categorical and numerical. First of all, number one, we really don't deal with ordinal variables too much because that gets into what's called non-parametric statistics. We're dealing mostly with parametric statistics. Usually when we deal with them in this course, we're dealing them as if they were categorical variables. So really categorical variables, numerical variables. So we looked at categorical variables and numerical variables together. And we've looked at categorical variables and categorical variables together. So what's missing? Numerical variables and numerical variables together. Okay, so like for instance, if we have a numerical variable like BMI, what's the probability that you would have high blood pressure? Well, if the data says for 100 subjects, we have the blood pressure and we have their BMI, we want to see if there's an association between the two. So we can't find, it doesn't make sense to find the average blood pressure and the average BMI because you can't, there's apples and oranges. You wouldn't be able to compare them anyway. So we want to know if you have a low BMI, are you likely to have a low blood pressure and a high BMI, high blood pressure, and so on. So that comparison of numerical to numerical variables is called correlation. When we go to compare the two of them, we are observing a correlation. We're looking to see if we can observe a correlation, association between the two variables. If this one goes up, does the other one go up also? If this one goes up, does the other one go down? A negative correlation. Or is it just random? We can't really tell what happens with one in terms of what the other one is. Okay, and then if that isn't enough, we can then branch over into another type of statistical test with those kinds of variables called regression. And in regression, we can really mostly we're going to work mostly with numerical variables, but there are forms of regression where we can use categorical variables also, okay, called logistic regression. But with regression, we're not only trying to establish whether or not there's an association between two variables. In other words, as one goes up, the other one goes up, right? But we also want to establish what that relationship is numerically. In other words, how much of an impact does one variable increasing have on the other variable increase? If you can imagine it as a line drawn, it would be the slope of that line, upwards or downwards. And that would tell us a lot about the relationship between those two variables. Okay, and that's called regression. Those two topics, correlation and regression, are going to be our last topics for the semester. Okay, when we come back from exam 2, we're going to be working on correlation and regression. It's going to be very interesting stuff, and it's going to be stuff that is really important in terms of many of the studies that you'll be reading. Perhaps if you wind up doing capstones where you're working with numerical data, they may be important to you then as well. Okay, so let's get down to the nitty-gritty here and see if we can actually do a little bit of work here. So I am going to, let's see. I'm going to open up this North Carolina birth file. And this again was, I shouldn't have done it that way. It's going to open up the wrong version of SPSS. I'm going to open this up. Okay, don't worry about that message if you see it. It means that the data set may have been created in a different version, and it's just letting you know that it has to update the data set, but it's not a big deal for us. Okay, so here is data about the mothers, 800 mothers, 800 randomly selected mothers from births in North Carolina over the course of a year. There might actually have been tens of thousands of births over that period of time, but this is a sample of random sample of 800 of those births. And we have a whole series of different kind of variables here. You may notice that some of them, age, for instance, you can imagine that's the mother's age, right? And you can see that's numerical data. You know, it's the actual age of the mother. Gained is the weight gained by the mother. T ounces is the birth weight of the infant, and T grams is the birth weight of the infant, also in grams. But a lot of these other variables are categorical. For instance, the plurality is the number of infants born. In other words, 2 would be twins. Sex is the gender of the baby. This marital is the marital status of the mother. So that's a categorical variable. Marital status is a categorical variable. The race of the mother is a categorical variable. Whether the mother is Hispanic, that's a separate categorical variable. Whether the mother smoked during pregnancy, whether the mother drank during pregnancy, and so on and so forth. We have a couple at the end here with the ethnicity of the mother, a slightly different grouping of ethnicities, and whether or not the infant was born prematurely. In other words, that's a yes or no. In other words, we know the number of weeks of gestation, right? But we've taken that data, and there's a new variable here, which tells us just yes or no, was the infant born prematurely or not born prematurely. So let me see if I can find a really low birth weight here. A really low number of weeks. 39. So this is arbitrary. In other words, you could have taken a cutoff. So here you can see that there is going to be a difference here. This is 7. Where did I just see 17 weeks? Did I scroll past it? Yeah, there it is. I lost it again. I saw 17 there. I know it. I'm not going to look for it right now, but take my word for it that that's what they're based on. In SPSS, if I go to I'm looking at SPSS in the data view, and I've opened up a file which was created by someone else. Okay, actually, we created it maybe in a previous class based on the information that we had. So originally, this data, when it was input into a computer somewhere, presumably, this data, we didn't actually see the gender of the mother, of the infant. We didn't see the marital status of the mother. What we saw instead was, I'm going to go here and I'm going to go to turn off value labels, toggle it off. We saw numbers like this. In other words, 2 and 1 represented the marital status of the mother. What we had to do is go to a code book and look up, what does 2 represent for marital status? What does 1 represent for marital status? You'll notice if I hover, it'll come up. See, it just came up. Now it's making a liar out of me. Come on. Well, I'm not going to wait for it. So we actually had to go to our code book, which explained what these the numerical variables are just numbers. So there's no categorizing them But the categorical variables, our input is numbers because it's more convenient to do that. It's less work. And number two, it cuts down on errors. In other words, as far as gender is concerned, if we typed in male or female, if one person used capitals, the computer wouldn't recognize it as the same thing as another person using lowercase. So it's better to just put it in that manner. So if I go to the variable view here, you can see that the variable name is listed in the first column. The variable name, each one of these rows represents a column in the data view. Okay, so there's 15 columns in the data view, so there's going to be 15 rows in the variable view. Each one of these rows, each one of these columns, rows rather, represents a different variable. So for mother's age, for instance, that's a numerical variable. So if I go across here, you'll see it says scale or scalar variable. And you may also notice that under values, it doesn't say, it says none. It doesn't bother saying anything. Weeks of gestation, same thing. Now, the other thing you may notice about this is it's a little cryptic. The variable names are a little cryptic. SPSS variable names have to start with a letter and can contain letters and numbers, but no special characters and no spaces. So it can get a little awkward looking at these and trying to translate them into what they actually are, like M-age, for instance. We know it's the mother's age because I mentioned it, but someone else may not recognize that. So if I go across here, and by the way, numeric just refers to the form that the variable is typed in, like numbers. Okay, not that it's a numerical variable. That's down here under measure. Okay, the width, what the maximum width of that value is going to be, and whether or not it's a scale, whether or not it has decimal places. So this is all whole numbers that we're dealing with here, except for the weight in grams, which when we look at the data, it's probably going to say decimal place, and most likely, since it's probably just grams anyway, 2 decimal places. We could actually change that to 0 if we wanted to, if we think individual grams is enough. The next column is label. So since the variable names are so limiting in SPSS, we can assign a label for them instead. And the label can be much more descriptive. So for instance, M-age can be the age of mother in years. Okay, now that's much more descriptive to anyone else outside of us that would see that variable, see the average for the M-age and so on. That would make more sense to them. So what happens is that if we apply a label, if we don't fill this in, if we just leave it blank, then SPSS will use the variable name, M-age, for instance, for any charts or graphs that it's going to produce. On the other hand, if we fill this label in, anytime it produces a graph or chart, it's going to substitute age of mother in years for M-age. Okay, so that's going to help us out quite a bit. Then as we move along, if we look at for instance, the marital status of the mother, I'm going to go across here, and again, the value that's actually going to the label that's actually going to show that in any reports that we do is marital status. If I go over here to value labels, it's a nominal variable. You can see over here, marital status, you can see it's a nominal variable. SPSS has recognized it correctly. If it didn't recognize it correctly, you could change it right there to something else. Okay, so, but it is a nominal variable. And since it's a nominal variable, we need to tell SPSS what those values represent, those numbers that have been typed in represent. So in this case, 1 represents married and 2 represents not married. Had there been a third value, we would type it in here and say single, or let's say divorced, right? And we would add it. Now SPSS would recognize what 1, 2, and 3 represent. Well, I'm going to take that out because it's not in our data set. Okay, and the way that we know what this is because we're working from a code book, a chart or an Excel file or a Word file that tells us that the variable values for marital status are 1 equals married and 2 equals not married. So we're not making it up. It actually is what the data represents. So now I'm going to go to my data view again, and let's take a look at what we might do in terms of some of the various kinds of statistics that we would be interested in. Let's say that we're interested in what is the average number of weeks of gestations for babies in North Carolina during 1982, whenever this thing was taken, right? What's the average? Well, we're never going to know what the real average for all 30,000 women is, right? We're only going to know what the average for this sample is, and we're hoping that the average for this sample will approximate the average for the entire population since we sampled them randomly. So let's give this a try. Analyze, descriptive statistics. I can go into descriptives, and I can ask it to calculate for me the average age of the mother. I can go into options. It's going to calculate the mean, the standard deviation, say the range, and I'm going to leave it at that for now. And I'll click OK. So as it happens, there are 800 women in this study. We knew that already. All of them are represented. There's no missing values. The range was 15 years old to 42 years old, which is a range of 27. And the average age was 26.92. And the standard deviation for all of the mothers was 6.107. Well, that's great, right? That's not a big deal, but that's something that we've learned how to do. Well, what is there? It's nice to know that the mean of this sample is almost 27. Are we really interested in the mean of the sample? What are we really interested in? We're never really interested. Well, the mean of the sample is just a means to an end, right? Without turning it into a pun. Right? So means to an end. We're really interested in the mean of the population. Does this tell us the mean of the population? Well, we don't know because we're never going to know the mean of the population without actually measuring everybody. But what we can do is we can make a judgment about how close are we, or where is it based on this variability, based on the fact that the standard deviation is 6 for our sample of 800 women, based on that the mean is this number for the sample of 800, very large sample of 800. What can I say about the true population mean? How can I best describe what we know about the true population mean? Well, what I can do is I can go into Analyze, Descriptive Statistics, and go into Explore, instead of Descriptives, Explore. And I can say, okay, let's move the age of the mother into the dependence list. Let's go into Statistics. Oh, well, look, one of the options that I have, it's going to do all the descriptive statistics. But one of the options I have is to ask it to calculate the confidence interval for the mean of our sample, so mean of our population. So often we're going to want 95%. Okay, and you guys remember, if we did it by hand, we would use the z-score times the standard error. We calculate standard error and so on and so forth. And this would be, and for a large sample like this, we would probably wind up using a z-value of 1.96 or a t-score that's very, very close to 1.96 because the sample size is so big, right? If the sample size is small, our t-value would be based on the number of degrees of freedom, the sample size, and our confidence interval would be the mean of our sample plus or minus whatever our t-score was for that sample size times the standard error being calculated by the standard deviation over the square root of the sample size. So I'm going to ask it to calculate that 95% confidence interval for me. I'll click OK. SPSS. Now it repeats what we just did, and it tells us, of course, that the mean indeed is 26.92, same result. And it tells us that the standard deviation is 6.107, same result as we got before, except with Explore now, it tells us also that the median is 26. The median is lower than the mean. So what does that tell us now? The average is pulled to the right skewed compared to the median, the middle. That tells us that the average age of the women are skewed to the right. In other words, there are more women that are considerably older than that than there are that are younger than that. So what else can we get out of this? We got a range, we got maximum, minimum range, interquartile range. Well, let's take a look at this. Here's our 95% confidence interval. So now not only, it actually calculates our standard error as well. Remember, standard deviation over square root of n. calculates that and uses that to calculate a confidence interval. Confidence interval is 26.49 to 27.34. I'm just going to round that off to 26.5 to 27.3. Okay, so although our mean for our sample of 800 women is 26.92, our 95% confidence interval for the true mean of the entire population is 26.5 to 27.34. Right? So we're 95% sure that the true population mean is between those two numbers. So we're much better informed about what the true population mean is, rather than just have a single number that we don't know if it's the population mean or not. Well, what does that mean, 95% confidence? That means that we're 95% certain that the true population is between these two numbers, not 100% certain. I could have done this, put in 99%, and we would have wound up with a different confidence interval. Would the confidence interval for 99% confidence be wider or narrower? Wider, exactly. Because you need it to be wider, because wider makes you more confident that you've captured the true population mean. Okay, so, and how about when we calculated it? What would make it wider? What would make it wider is that the t-score or z-score, depending on which one you used, would be a larger number for a 99% confidence interval than a 95% confidence interval. So t times the standard error, if t is a bigger number, that's going to be a bigger number. That's going to be our margin of error. Bigger number we add and subtract from the sample mean is going to make it a wider confidence interval. Okay, so what do I do next? Well, let's say I have done a study of women in New York State. And in New York State, I found that we actually, in New York State, we have a lot of, in North Carolina, they don't have much of a budget, right? New York State, we have unlimited funds to do healthcare studies and stuff like that. So New York State, we actually recorded the age of every birth in New York City. I don't know, they probably do that, I would think, right? I'm sure they record every birth. The question of the age of the mother, I'm not sure if that's on the birth certificate or not. Probably is. I'll bet you it is. What's that? You think so?
Date of birth of the mother.
Yeah. Oh, they probably have date of birth. You're probably right. Probably has date of birth of the mother. Okay. So may not have the weeks of gestation. That might be somewhere. That's in, because of different hospitals. Who knows if there's a place to get a single record? But I'm thinking there is. We're going to be talking about New York City Community Health Survey. New York City maintains a lot of health records. A lot of them you're probably not aware of, and there's a good chance that because of an initiative that started a number of years ago, that a lot of these records now, a lot of this data is publicly available. So you can actually go online and actually look this information up. And we're going to be taking a look at that. Maybe we'll find something like that. Okay, but we'll take a closer look at that in a little while. So at any rate, so let's say I knew what the average birth weight was for women in New York State, and it turns out it's 26.5 years. Okay, so I'm going to go up here to Analyze, and I want to compare the mean for women in North Carolina to the mean for women in New York State, mean age of the mother at birth. Okay, so let's see. In New York State, I know what the mean is. It's equal to 26.5, I think I said. Yeah, 26.5. In North Carolina, I don't know what the mean of the population is. I only know the mean of the sample. So in one case, I know the mean of the population. The other case, I know X bar, the mean of the sample. So that is a single sample t-test. In other words, we know we have a known mean, and we want to compare our sample mean to our known population mean. That's one sample, but it's two means, but it's one of them is a sample, the other is a population. So I'm going to go over here to Analyze. I'm going to go down to Compare Means, and I'm going to say one sample t-test. And when that comes up, I can tell that I'm interested in looking at the age of the mother in years, And I want to compare that to a known mean of 26.5. SPSS now is going to run a t-test. It's going to compare these two, see how many standard errors apart that they are, and to see if we can reject the null hypothesis. And our null hypothesis here is that the mean of mothers in mean age of mothers in North Carolina is equal to the mean age of mothers in New York State. Okay, and our alternative hypothesis is that they're not equal. So mu New York is equal to mu North Carolina, or I'm sorry, mu North Carolina is equal to mu New York, or alternatively mu North New York North Carolina is not equal to mu New York. Well, since we know the mean for New York is 26.5, we could just substitute that in our null and alternative hypothesis and say null hypothesis mu for mothers North Carolina is equal to 26.5, or mu for North Carolina is not equal to 26.5. So we could actually just substitute that. And that further indicates that it's a single sample t-test. Well, let's say, okay, and see what we get. Okay, so here's what we get. We get a t-score of 1.922. Now we have to determine, is that above the critical value of t that I need to reject the null hypothesis that the two means are different, right? Well, if it were a z-score, what would it have to be? In other words, if it was an enormously large sample and we could just use the z-score, what would the critical value of z be for 5%? Now for 5%, it would be 1.96 exactly. So this doesn't exceed 1.96. So even if I use the z-score, it fails to reject the null hypothesis. Now, degrees of freedom is 799. If I had such a table, I could look up what the critical value of t is for that, but it's going to be very close to 1.96 anyway. Right? So again, we're going to fail to reject the null hypothesis. Well, let's take a look at the significance. This is the probability we would get this big a difference, then this amount of standard errors apart for the two means if the null hypothesis were true. So the chances of the null hypothesis being true, if it got that big a difference, is 5.5%. Well, what is our acceptable alpha error level in say most of these studies? It's 5%. So we have a greater risk of being wrong if we reject the null hypothesis than we want to tolerate. So because the t-score is less than the critical value, because the significance or p-value, probability of this outcome, if the null hypothesis is true, is greater than 5%, we fail to reject the null hypothesis. Okay, so I'm going to take this one step further. That was a single sample t-test. Now, let's take this same data, analyze. I'm going to go to compare means again, except this time I'm going to do independent samples t-test. Now I'm comparing two groups to one another, okay? Two samples to one another. So let's see. I'm going to still stick with the age of the mother, except this time I'm going to examine whether the marital status for these two, whether the average age for married women is different from the average age for unmarried women. So I'm going to move married women into the grouping variable. So what would our null hypothesis be here? Our null hypothesis here is going to be the mean age of mothers that are married is equal to the mean age of mothers that are unmarried, right? So in both cases, it's a sample. So would I, in my null hypothesis, would I use X bar equals X bar mothers, X bar for married equals X bar for unmarried, or would I use mu for married versus equals mu for unmarried? What do you think for a null hypothesis? They're both samples. They're both samples, but the key here is we're not really interested in the difference of samples. We're interested in the population differences. Right? That's why it's a probability. I mean, if we were going to sample both populations entirely, then we would see the averages. There'd be no probability. We'd see what the two numbers were, and we wouldn't have to worry about hypotheses and probabilities and stuff. But since we're only working with samples, we do have to worry about that. But the key here is that our concern is really with the populations, not the sample. So our null hypothesis is mu for this group is equal to mu for this group, and our alternative hypothesis, mu for this group is not equal to mu for that group, even though we're working with two samples. So you'll notice that the grouping variable comes up with question mark, question mark. That's because SPSS doesn't realize that there's only two groups here. So it's asking me, it could be more than two groups, like married, single, married, single, divorced, widowed. It could be four groups, for instance, right? So since I'm running a t-test, I can only do with two groups. It's asking me, well, do you want 1 and 3, 1 and 2, 1 and 4? In other words, married and single, married and divorced, right? So that's why it's asking me this. You would think $4,000 program, it would be able to figure out there's only two groups in this, and it wouldn't ask me that. So I don't remember which the numbers are. I'm going to guess 1 and 2, not 0 and 1. Whoops, I didn't mean to do that. Okay, let me go back to, oops, I'm in Safari. Hang on a second here. Okay, so I'm going to click continue, and I'm going to go ahead and do this test. I think in options, yeah, options, again, I get to put 95% or 99% if I want an alpha of 0.01. I'm going to click OK. And let's see what happens now. Well, first of all, I get an extra box here. That extra box actually analyzes the two groups separately. It factors them into two groups. Okay, so when you factor them into two groups, what do we wind up getting? We wind up getting the married women have an average age of 29. The unmarried women have an average age of 22.65. Okay, probably not a surprise, right? Probably that might have been something we might have predicted. Might even be something that we might want to prove, for instance, or attempt to prove. So what about the variability in the two groups? Well, the variability is about 5.3 for the married women and 5.4 years for the not married women. So they're really pretty damn close, the two variabilities, right? So we had that chart that told us use these formulas if the variables are equal. If the variability is equal, use these other formulas if the variables are different for independent samples t-tests. Okay, so, and I'll pull those up later on, that chart, just so you know which chart I'm talking about. Okay, so this is an independent samples t-test. And we had it when we went to that chart, we made up our mind based on this, whether or not we were going to say we were going to use the formulas for equal variances or unequal variances. And our general rule was that if the standard deviation of one group is not double what the other one is, then we're going to say that they're equal. We'll assume they're equal, and we'll pool our variabilities. If they're more than double, one is more than double what the other one is, we're going to say that they're unequal. Well, in SPSS actually does a statistical test to determine whether or not it should use equal or unequal. Okay, and if you look at the output I have down here, instead of running like we would if we're doing it manually, we would make that decision ahead of time that, oh, I'm looking at standard deviation. Before I run the t-test, I've decided that, you know, I'm going to use equal variances or unequal variances. So I'm only going to run one result. SPSS actually runs both results. It runs the equal variances assumed in the top row of its output, and equal variances not assumed in the bottom row of its output. So if I look at this, I see that the t values are very similar. They're a little bit different, but they're very similar. But look, the degrees of freedom are different, and probabilities. Well, probability in this, the sample size is so big that the probabilities are both the p values are both less than p equals 0.1% of 0.001, less than 0.001. Okay, so the big t value and this tiny p value or significance way below 5% tells us we're going to reject the null hypothesis in either case. But which of these two rows would we have used if there was a difference, right? And in smaller samples, they're likely to be a different. Okay, so let's take a look at this. You may notice that there's a very tall, skinny line right here where I'm running the arrow up and down. And on one side of that line to the right is our t-test, all of our t-tests. On the left side of that line is a test called Levine's test for equality of variances. In other words, a test to determine whether the variances are equal. Okay, and you can see that over here we have a value for the statistic and a probability, a significance or a probability. And again, just like the t-test, we're going to start with a null hypothesis. We start with equal variances assumed. Variance for group A equals variance for group B, just like any other null hypothesis. And then we're going to come up with a alternative hypothesis, equal variances not assumed, equal variance different, which would be the bottom row. Okay, so now how do I choose which one of these to pick? Well, we start with the assumption that the null hypothesis is true. And then we go over here to our F value, which determines what our significance, our probability is. And if this is less than 0.05, we reject that null hypothesis and accept the alternative that the variances are not equal. And then we use the bottom row in that case. In this case, it's greater than 0.05, so I fail to reject the null hypothesis, so I stay in the top row. So our t-value would be 15.836, and our significance would be 0.000, 0.00, less than 0.001 really. So we would reject the null hypothesis, accept the alternative hypothesis, that there's a difference in the mean age for married women versus unmarried women in North Carolina in 1982 or whatever it was. Okay, so, okay, now paired samples. What about paired samples? So we can come up with a notification. Okay, I don't need that. Okay. Where is it? Here we go. This if I can't find. Here's a sample of paired samples. Okay, here's a version of it. I'll go open with SPSS. Okay, so I open a new file. Oh, it's opening in another version. Oh no, it's okay. We're okay. So we've opened up a new file. Paired samples. And where's the window? Why don't I see it? That's my output. See statistics. Oh, here we go. Okay. Still don't see the window. Oh, maybe it's. Why is it hidden? What's that? Oh, no, don't tell me it did that again. I thought I told it to open up in 25. Okay, yeah, there's more than one version open right now. That's that. I don't know. Okay, let me try this again. Open with version 25. Try it again. Looks like it's down here. Nope. What's really fighting me? Okay, I'm going to do it the better way. And oh, here it is. Oh no, you're right. Open up another version. Now I don't know which one to close. Nope. Maybe it'll close on its own. Go away. Come on. Okay. Let me close this. Yes. No. Okay. So I'm just going to drag this onto my desktop so that I have it on my desktop and I can open it. That's just as simple. I could have just probably typed these numbers in the amount of time that this has taken me. Okay. back to SPSS. I'm going to open a new data set. Open data, navigate to my desktop. Okay. Here it is. But it's fighting me every way it can. Gotta be here somewhere. Again, it's opening in the wrong version, I think. Oh, I see it there. No, I don't see it there. Kind of weird, right? You know what I'm going to have to do? I'm probably going to have to close this and open it separately. Yeah, that won't let me open it. Save changes. Data set. No. Here we go. I'll bet you this is it now, too. I can get to it now. No. Okay. Oh, what are these down here? Oh, there it is. Look at this. That's interesting. That's a new one. All right, hit them down there. Okay, here we go. All right, so this kind of describes the study I was talking about before, where you have patient number one, took the blood pressure medication. It lowered his blood pressure 6 points. He took the drug, lowered it 6 points also. So he saw no difference. So the difference would be 0 for him. But this guy took the placebo and his blood pressure was 7, dropped 7 points. This one dropped 5 points. With the drug, dropped 5, so on and so forth, 8 and 5, 9 and 12, and so on and so forth. But really, the difference we're interested in for each individual patient, what was it before with the placebo versus with the drug? So we're really interested in the difference between all of those things, right? So each one of these numbers represents the same subject. It's not two different groups. One person, one of 9 people taking the placebo, and one of 9 people taking the drug. 9 people taking the drugs. Not two independent groups. It's actually the same people taking both regimens for a period of time. So now I want to compare the two of these. So the way I would compare them is to subtract 11 from 12 for -1, 12 from 6 for 6, 13 from 12 for 1, 14 from 11 for 3. And then I would examine whether the average difference is different than 0. So our null hypothesis would be that the differences are equal to 0. Our alternative hypothesis is that the differences are not equal to 0. So let's take a look at that. Analyze and compare means, except this time it is a paired samples t-test. Okay, and in this case, it waits for me to enter 2 variables, right? Because you need 2 variables, it's got to compare them. So this is each person with the placebo, and this one is each person with the drug. And click OK. And it actually should do the analysis for us. Let me see where my output window went. Okay, here's my output window. And my output window tells us that with the placebo, the mean was 10.0, with the drug was 8.44, so on and so forth, 9 patients. And if we go down here, the mean difference, the average difference, each individual difference, and then the average was 1.556, right? Remember, the null hypothesis was that mean difference, placebo minus drug, was equal to 0. So it came out to 1.556. The standard deviation was 2.96. the standard error was the square root standard deviation over the sample size, which was 9, right? It comes out to 0.899. And the 95% confidence interval, the 95% confidence interval for the difference between the two of them is minus 0.5 to plus 3.6. So what did we say that the null hypothesis was? That the difference was equal to 0. And our alternative hypothesis is the difference is different than 0. So if our confidence interval contains 0, 0 is within our confidence interval, then the null hypothesis could be true, at least at a level of certainty that we are interested in. So we fail to reject the null hypothesis because we can't say with 95% certainty that it's not 0, because 0 is included in our confidence interval. In other words, where we expect the mean to be if the null hypothesis is true. And if you look at the t-test for this result, t is 1.730. That's a small value. It's way less than 1.96, or what the critical value of t would be, a sample size of 9. Critical value of t for sample size of 9, 8 degrees of freedom, is probably something like 2.3, right, from our t table. So t is 1.7. So that's, we don't exceed t, another argument for not rejecting the null hypothesis, because we didn't exceed the critical value of t. And then finally, the probability of getting this big a difference, this big a t-score, if the null hypothesis were true, is 12%. And we only want to reject the null hypothesis if the probability of its being true is less than 5%. So this had to be less than 0.05 for us to reject the null hypothesis. So that's our last t-test, our paired samples t-test, if you use SPSS to do this work. Previous examples of this, we've done it manually. In a number of other situations, we have recordings of it online where we've done it manually. And just to remind you of what it looks like when you do it manually. Let me go here. T-test. Here we go. Okay, let me go to the data files. Okay, here you go, t-test variations. Okay, so here's a document that says, comparing the means of two populations using hypothesis testing. This is standard sample deviations are assumed to be sample standard deviations assumed to be equal. These are the formulas we use. We calculate a pooled standard deviation and then use that to calculate our t-score down here. And n's are the sample sizes, and x bar 1 and x bar 2 are the sample means. And the next page is, well, what if the standard deviations are not assumed to be equal? Well, then we would use this formula for our t-value, standard deviation of group of sample 1, standard deviation of group sample 2 squared over the samples divided by sample sizes added together, square root, and the difference between the two means on top would give you a t-score. Your degrees of freedom to calculate to look up your critical value uses this really nasty formula. A lot of cases, because it's so nasty, we just take the smaller sample size and subtract 1 and use that for degrees of freedom. That's very conservative. Okay, I think it says that. Smaller sample size times 1, yes. Okay, and then finally, we also have a calculation for the differences between two proportions, a t-test for proportions, basically, where P1 is a proportion of one group, P2 is a proportion of the other group. For instance, the proportion of Frenchmen who have heart disease versus the proportion of Americans who have heart disease. Those would be the two proportions, and you can use them along with the sample size to determine what the z-value is for your analysis and see if that's greater than or less than the critical value of z, which is 1.96. Why do we use z again instead of t? Why don't we bother with t when we're working with proportions? Well, it's because our sample sizes are typically very large when we're doing studies with proportions. Okay. So, okay, so anyway, so that's where that document, that's where the comments came on that. Okay, so I'm gonna take a 5-minute break so I can drink something, get my voice, keep my voice going. And you guys probably take a break from listening to me too. Let me pause.
This conference will
All
now
right,
be
so we're
recorded.
back. And now the next thing that we worked with is the idea of comparing more than two means at the same time. And for that, we use analysis of variance. So I am going to go into SPSS again. And let me see if I can get to the window here. Here we go. And again, it must be hidden down there. Nope, don't need that one. What about this one? No, also. So many windows open here. Let's see it. Nope, not what I want. I'm going to do this top here. And I don't want that one. Whoops. Now, and just a moment, we should be back up here. Oh, I got the wrong version again. Keep switching the one in the taskbar, but it keeps coming back to the original version. Okay, let's try this. Okay, that should work now. Okay, so our next topic is a situation where we have more than two means we want to compare. Analysis of variance. So for instance, in this data set, I'm going to pick out a categorical variable that has more than 3 values. So let's see here, race of the mother. Okay, we've got many values there. Actually, I think that might be a little bit of a problem. Let's see whether the mother is Hispanic or not. Or let's see, how about ethnicity of the mother? Okay, well, ethnicity of the mother, we have 4 groups indicated by 1, 2, 3, and 4. So let's say I want to see if the average age of Hispanic mothers in North Carolina is the same as the average age of Black women, as the average age of white women, and average age of all other women averaged together. Okay, so that would be analysis of variance. I could use the t-test for any of those two groups and any other combination that I wanted to, but I would be a lot more work, and I would introduce extra probability of error by doing it over and over again with a 5% chance of improperly rejecting the null hypothesis. So instead, I am going to use SPSS to solve that for me using analysis of variance. So I'm going to go into analyze. I'm going to go into compare means because that's still what I'm doing. And I'm going to go down to one-way analysis of variance. And again, if you go back through the videos from the week when we covered this, you'll see that really analysis of variance, even though it says it's talking about variances, is actually comparing means. So what it's doing is it's looking to see what the mean is, what the average is between groups, the difference between the averages of groups, and the amount of variability within each group. So it's the variability between groups and the variability within each group, so that you can tell whether or not you can be certain that the means for the populations are different. So again, null hypothesis would be mu1 is equal to mu2 is equal to mu3 is equal to mu4 equal to mu-n. And the alternative hypothesis is that at least two of those means are different, right? Not all of them, but at least two. So I'm going to say one-way analysis of variance, compare means. And I am going to, again, look at the age of the mother as my numerical variable. And I am going to put in the ethnicity of the mother, 4 groups, into the factors. Notice it doesn't bother to ask me to give it the values because it knows I'm going to use all of them now, all 4 of them. Okay, so now I know that if we can reject our null hypothesis that all of the means are equal, are the same, right? If we can reject that hypothesis, I'm going to want to run post hoc tests, but I'm not going to run post hoc tests until first I can reject the null hypothesis. So I'm just going to go ahead and say, okay. And what do we get? Well, we get the variability between the groups and degrees of freedom, because that's the variability between the groups, the means themselves, divided by the degrees of freedom is 3, gives you the mean squares, the mean sum of squares, the variability between the groups. The variability within the groups, the sum of squares divided by the degrees of freedom. That's because there's 800 women there minus 4 groups, that's 796 degrees of freedom, and that mean is 34. Okay, and the F statistic, the analysis of variance statistic, is the mean sum of squares between the groups of the mean sum of squares within the group. Okay, and that's equal to 809 over 34 is 23.5. That's where this number comes from. And that 23.5 is our value of F for this study. And if we go to our table for analysis of variance, we will see that the critical value of F might only be 2 or 3. Let me see if I can't get to that easily. Okay, let's see if I got it here somewhere. That's not showing up. Oh, I mean analysis of variance. There we go, there it is. So here's our analysis of variance table for critical values. And this is for a probability of 0.05. So our degrees of freedom is for the number of between the groups, there's 4 groups. So our degrees of freedom is 4 minus 1 is 3. Okay, so that is our column that we're going to use. And for the number of values within the groups, well, it's very large. So I'm just going to go all the way down to 120 for each group. It's well more than that, but it's not infinity. So I'm going to say 120. And I'm going to go across, and my critical value of T for F is 2.68. So if I go back to my analysis, you can see that we've exceeded our critical value. It's big enough that we can reject the null hypothesis. So now we know at least two of these means are different, but we don't know which ones at this stage. So now we go back and do our post hoc test. Analyze, compare means, one-way analysis of variance. And now I'm going to go to post hoc. And again, we discussed this. I'm going to stick with Bonferroni or Tukey. They're relatively conservative post hoc tests. There's a lot of reasons why you would use these others as well. But for our purposes, any one of these relatively conservative forms of the post hoc tests are fine. So I'm going to click continue and OK. And now SPSS, it will repeat the analysis of variance, gives you the same value, except this time it's going to compare each one of the different permutations in comparing the means. So what we're looking for is a significance, a probability of getting this big a difference if the null hypothesis is true. In other words, the means of the two groups are true, and we want that to be less than 0.05. So we can say that the mean age for white mothers is different than the mean age for black mothers. The mean age for white mothers is statistically different than the mean age for Hispanic mothers, less than 0.05 different probability. Okay. Can we say that the mean age for black women is different than for Hispanic women? Yes, we can. Can we say the mean age for non-Hispanic white women? Well, we already did that, didn't we, when we did it up here? See, it kind of doubles. It does a test twice for each group. Non-Hispanic black women versus Hispanic women, can we say that those two are different? Well, no, we can't, because the significance is not less than 0.05. So you can go through all of these and determine which of these are different. Okay, and there is one that's just barely squeaked by here, which was this one we failed on, Hispanic versus all other groups, right? Not less than 0.05, but other versus black women, there is a significant difference for the age of the mother there, less than 0.05. P is equal less than 0.05. So that's the way we would use analysis of variance and the p-value for the analysis of variance itself to justify using the post hoc test. And in the post hoc test, determining which ones of these pairings have a probability of significance of less than 0.05. Okay, so now what about categorical variables? The last frontier, at least for this series, right? At least for this group of tests. Okay, so let's take a look at a couple of categorical variables here. How about something like marital status, which is a categorical variable, married or not married, versus, how about this nominal variable, premature infant. 0 represents infant was not premature, and 1 represents the infant was premature. So I am going to go, I want to compare the two of those. So, well, let me see what else we got. Okay, not wait. Child. And smoking. Okay, so let's examine whether or not smoking had any influence on the probability of a premature birth. So smoking, the variable smoking or smoke, right, had two values. Either the mother did not smoke during pregnancy or the mother did smoke during pregnancy. And the variable premature birth had two values. Premature, 0, and infant was premature, 1, infant was not premature, 0. So I'm going to compare those and see if there's an association between the two of those. So since they're both categorical variables, I'm going to attempt to do a chi-square and calculate odds ratio. And how do I get there? Well, I'm going to go into descriptive statistics because the first thing I need to do in order to do this is to set up a crosstabs table. So the exposure is whether or not the mother smoked. So I'm going to put it into the rows. Oops. Let's see. Smoke during pregnancy, I'm going to put it into rows. And the columns I'm going to put in the outcome, whether or not the child was premature. Oh, and it tells us, it defined it as less than 36 weeks. We were speculating about that a little bit before. So I'm going to go over to cells. I'm going to tell SPSS I wanted to calculate the observed values and the percentages by rows. We could calculate the expected values. We could make two tables, the observed values and the expected values tables, right? If we were doing it manually in Excel, we would need to do that. If we're doing it in SPSS, SPSS will do that on the way to doing the chi-square calculation. So I'm going to say continue, and I'm going to say okay. So we're going to wind up with a 2x2 table. Here's our 2x2 table. And in our 2 table, it says that 86% of the mothers who, 11.4% of the mothers who had did not smoke had a premature birth. And among mothers who did smoke during pregnancy, 13.2% had a premature birth in this sample. Okay, so that suggests maybe that they're not equal. So what would our null hypothesis for a analysis like this be? Well, a null hypothesis, we're not comparing means, but so our null hypothesis would be that there is a null hypothesis that there's no association between smoking and premature birth. And our alternative hypothesis is that there is an association between smoking and premature birth. Naturally, again, we want to be able to reject the null hypothesis in order to accept the alternative hypothesis. That's why we phrased it that way. So in this case, we would calculate a chi-square value. So I'm going to go in here and say analyze, and I'm going to go to descriptive statistics and crosstabs. And we would, if we were doing it on paper, we would calculate for each one of the boxes in the 2x2 table for observed values, and the one we created for expected values, we would subtract observed minus expected, square it, divide by expected, put that number aside, do it again for each of the 4 boxes, add the 4 numbers together to get the chi-square statistic. I'm going to click OK. And our chi-square, I didn't tell it to do the chi-square analysis. Analyze descriptive statistics across tabs. Got ahead of myself there. And okay, and I'm going to go into statistics and ask it to calculate the chi-square value. And I'm going to say okay. And it calculates the chi-square value, and it comes out to be 0.292. Okay, what does that mean? That means that I don't exceed my critical value for chi-square, and my probability is only, kind of surprised given this big a sample, right? 13.215 versus, because this sample this is so small, it's just a small count. Okay, since our chi-square value is small, our probability, our p-value is small. So the probability that we would get this outcome if the null hypothesis is true is almost 60%. So in other words, this is not less than 0.05, so I fail to reject my null hypothesis. Well, let's take a look at these numbers. The probability that mothers who smoked would have a premature birth is 13.2. That's their risk. Okay. The probability of mothers who didn't smoke would have a premature birth have a probability of 11.4%, a risk of 11.4%. My relative risk is 13.2 divided by 11.4. So it looks like my relative risk is roughly 1.2, 1.1, 1.2. In other words, 10 or 20% greater risk for mothers who did not smoke. If I looked at it from the perspective of, unfortunately, premature was in the columns on the right, and not premature was a column on the left. So I'm really testing whether or not the odds ratio for being not premature. So you're more likely to be not premature if you're not a smoker than if you are a smoker. So let me go ahead and calculate the confidence interval, the odds ratio and the relative risk. Analyze. I'm going to go to Descriptive Statistics, cross tabs. And this time I'm going to go into Statistics, and I'm going to click off Risk. And I'll click Continue and OK. Let's see what our output looks like now. Our output now says, same result for chi-square, nothing's changed. But now let's look at our risk estimate. So this top row is the odds ratio for smoked during pregnancy versus did not smoke during pregnancy. So the probability of the increase in probability of not having a premature infant if you are if you didn't smoke during pregnancy is 17%, 1.7 times, or 17 or 18% greater if you didn't smoke. For the risk ratio, in other words, the risk of one versus the risk of the other is 1.02. Well, the important thing here is that our null hypothesis, when we're talking, as we spoke earlier, our null hypothesis when we're talking about odds ratio is if the odds ratio is equal to 1 or the relative risk is equal to 1, it means the risk of having a premature birth is the same for mothers that smoked versus mothers that didn't smoke. So our null hypothesis is that odds ratio is equal to 1. And our alternative hypothesis is that the odds ratio is not equal to 1. So we want to prove it's not equal to 1. Same thing with relative risk is equal to 1 is our null hypothesis. Relative risk is equal to 1 is our alternative hypothesis. So if I look at this, I say to myself, oh, it looks like the odds are better for having a non-premature birth if you are a non-smoker than if you are a smoker. Well, that's good. However, the 95% confidence interval for the true odds ratio is 0.65 to 2.12. So what's our null hypothesis? Our null hypothesis is that the odds ratio is equal to 1. But even though we calculated a value of 1.17 for odds ratio, we're 95% sure the real population odds ratio is between 0.65 and 2.128. In other words, 1 is in between those two numbers. So we can't reject the null hypothesis. Similarly with the relative risk, 1 is between these two numbers, so we can't reject the null hypothesis. So all three of these agree. The chi-square says we can't reject the null hypothesis because this is not less than, the p-value is not less than 0.05. The odds ratio and the relative risk also say don't reject the null hypothesis. Don't accept it, just say don't reject. Don't reject the null hypothesis because our 95% confidence interval for the odds ratio and for the relative risk both include 1 within that interval. So we can't say with 95% certainty that is really different than 1. Okay, so that's how, for the most part, we would use the chi-square statistic. So now, I want to introduce one other thing. And then maybe a good time to call it a day. Okay, that other thing I want to introduce is this idea that we have many databases online that we can take advantage of. So for instance, I can go to, okay, let's see what happened to I can New York City Community Health Survey. Maybe find it with just the initials. New York City Community Health Survey and Trends. Okay, let's go to this one. Here is the New York City Community Health Survey public use data. New York City every year does a phone survey of over 8,000 people, and it asks them a series of questions. Okay, let's go into 2018. Ask them a series of questions. In fact, you can actually download the actual questionnaire here. And it actually goes through how they actually, what the choices are, what the interviewer should be saying when they interview someone. Do you live in West Harlem? Let's see. May I please have the adult's first name? confirm just, okay, your zip code. In other words, it's a script really that they go through. And they ask these people a couple, like 100 or more questions about their health. If I go further down here, you'll start to see some actual health questions. What kind of insurance do you have? If you have insurance, do you have insurance? Do you don't have insurance? Have you ever been told by a doctor or a nurse or a health professional that you had asthma? Yes, no, I'm not sure, or a few. So we know now what the prevalence of asthma in the population is from self-reported asthma is. Further down here, you'll get information about, for instance, consumption of different kinds of foods, how many portions of vegetables, fruit and vegetables do you eat per day, how many sugary drinks do you drink per day, and so on and so forth. Do you drink coffee? Do you smoke? And so on. Okay. Do you now smoke cigarettes every day, some days, or not at all? So you have a whole bunch of data in here. A lot of this data is obviously categorical, but not all. On days that you smoke, how many cigarettes on the average do you smoke? And they would get an actual number there. So we have a combination of categorical variables and nominal variables as a result of this. And it's been done over many years, so we can actually see trends as time goes on. So the actual data set itself, oops, I shouldn't have closed that. The actual data set itself is here also. Before I get to that, I just want to show you your code book. The code book, the data set itself, let me go back. The data set itself is here. It's in SAS format, but that's okay because we can import SAS format into SPSS. Okay, and in fact, we have it available here. So I'm going to see if I can do this without causing a riot again. Let me get to SPSS and close this file. Okay, so now I can import SPSS, the SAS file into SPSS, and I've done it here. Here is 2018 New York City Community Survey.sav, fullset.sav. I'm going to open that. Open with the right version. Okay, let's see what we wind up with here. Well, my goodness, look at all of these things. Look at all these variables that we have here. We have 149 variables, okay, in our variable view. And here's the actual data itself. Oh my God, it's all numbers, right? Well, what are we going to do with that, right? Well, some of these variables happen to be numerical variables. Not many of them, but a few of them are. For instance, let me see if I can't find a couple. This one looks like a scalar variable. Okay, BMI. This is a scalar variable. It's a number. So you can find an average BMI, for instance. But many of the others got weight, so on and so forth. Many of the others. What the hell is this one? Everyday PDA. What does that mean? Okay. Well, remember I mentioned to you that sometimes the variable names themselves can get kind of cryptic. The way that you expand on that or label that so it's understandable is that you assign a label to it. So CPD18A, the number of cigarettes per day, every and some day smokers. Okay, so that's what that category stands for. That's what that means. And you'll notice that we need to tell it. Let me hang on a second. Let me make sure I get a categorical variable. Insured. For instance, insured or not insured. Insured, whatever that says, insured or not insured. Insured gateway 18. Okay, that variable. What is that? Well, basically it's the question, are you insured or not insured? Well, now we need to tell SPSS what those values are if we want to work with that data. Well, where do we get those values? We get it from the code book. Okay, and if I go back to my database here, you'll notice one of the options online was to download a code book. And there's the code book. Okay, so now in this code book, I can search for insured gateway 18. Well, what is it? That's question number 2-1. Do you have any kind of health coverage, so on and so forth? And the answers to that are 1 is yes, 2 is no, in terms of health insurance. So I can go back to SPSS, and I can go into SPSS and tell it now that 1 is insured, and 2 is not insured. We're talking health insurance, of course, not automobile insurance, not motorcycle insurance, not Geico, but just insured and not insured. Okay, if I go back to my data view, well, now if I scroll across, you'll notice that suddenly, actually I got to go up here to make sure its value labels are turned on. If I go to the right spot, you will find that, whoop. There we go. Oh, no, I don't see it yet. There it is, insured or not insured. There's our variable right there. Okay, so I've given you on Blackboard a version of this that you can play with. And in this version, we have narrowed whatever. Closing the vote. Do you want to proceed? Yes, I do want to proceed. No, I don't want to save that. Okay, in this version, this is from 2013. I may actually do something with 2018. You can do it on your own too, because you have the code book here as well. But in this version, what I've done is I have taken the full data set for 2013, and I narrowed it down to a handful of variables. I'm going to open this, open with 25. I'm going to take a look at it, and it's already been coded for you, so you can play around with it. Here you go. So let's see, borough. That looks like the borough that a person lives in. Go up here. Oh, you want to know something? It's not. I gave you the wrong version. It is not already coded. So we would have to go in there and put in the values. You know, I have another version of this with the values. I'll post another version of this that actually has the values, but it's narrowed down to the borough the person's age, the borough of residence, the race or ethnicity, the neighborhood, neighborhood poverty rate, whether the person's insured or not insured, the type of insurance, whether or not they received the flu shot in the last 12 months, their gender, their nativity meaning are they born in the United States or not, and the number of children under 18 living in their household. So if you wanted to, you could pick out a couple of these variables and try and see if there's a difference in the rate at which males and females are insured, right? That would be male and female. It would be insured and non-insured, 2 categorical variables. So that would be a contingency table, 2x2 contingency tables. You could do chi-square, and you could do odds ratio to see if there's an association between gender and whether or not you have insurance. On the other hand, you could see if there is a difference in the average age of people who are insured versus not insured. So insured or not insured and age, you have a categorical variable and a numerical variable. So you can do a t-test for those 2 groups. If there's a categorical variable with more than 2 groups, like maybe type of insurance, right, which might be Medicare, private, so on and so forth, you could do an analysis of variance to see the average age of people that are in each one of those groups, see if the means are different, right, and so on and so forth. So there's a lot you could do with this. So I will begin when we come back. after the test, I will be giving you a couple of databases like this. I'm going to fill in these. I'm going to find, I'm pretty sure I have another version already made up for 2013 that has all these categorized, have these labeled, or the values inputted. So I will post that if I can find it, or I will update this and post it so you can play around with it. But the key here is that after the exam next week, and the exam will be similar to exam one, you'll have two chances to do it. You'll have the average of 2 scores. You can use any of the resources that are on Blackboard or linkable from Blackboard. The only key is you must do it on your own. The only reason this works, that I can do this online, and that is the presumption that you will honor that and not go out and get help from someone else in completing the exam. After the first version of the exam, first trying the exam, you'll see which ones you got wrong. You'll be able to go back and redo the exam and get the average score of the average of those 2 exams. Now, after that, in the final 3 weeks, we're going to be covering correlation and regression. And instead of a final exam covering correlation and regression, you will have an option. You can either do another exam, or you can do a relatively modest project where I will give you a bunch of databases like this, and this one is on insurance and flu and various other factors, and you can put together a little study where, like, kind of a poster, where you describe what you're interested in researching, what your theory is, maybe look up a reference or two to some material that might enlighten the subject, and then make a couple of graphs that show the distribution of the data, maybe age distribution. In other words, describes your population, and then do at least one statistical test, just one statistical test of your choice. In this case, it might be comparing whether people born in the United States are more likely, whether or not being born in the United States makes you more or less likely to have received the flu shot in the last 12 months, or male or female to have received the flu shot in the last 12 months, or if you're insured or not insured, having received the flu shot in the last 12 months. So those all happen to be chi-square and odds ratio. But like I said, there's at least one variable here, age, that is numerical. Okay, next, the other data sets have some more numerical data if that's what you're interested in doing. So you'll have the option of doing a modest project or poster, and I'll give you a pretty thorough description of that once we're back again after the final. Second exam will be posted on Monday. You'll have a week to do it, right? So there won't be another session online that is like this, 3 hours, but I will set up a session or two where if you have questions, you have 2 ways to get feedback and get questions answered. One is I'll set up at least one additional session where we can have a Q&A. You can either email them to me or post them on Blackboard. I'll make up a spot on the discussions forum where you can post the questions. It's better if you post them to the discussions forum, because then I can answer them for everybody, and it's a somewhat fairer that way because everybody gets to see the clarification. And you can post for each other. As long as you don't answer the questions themselves, you can post maybe some helping tips without giving the answers away to the problems on there if people have issues with, remembering certain kinds of calculations or something like that. Okay, so I will, you have these, a couple of these on Blackboard already. I will post a version of this that's actually been coded so you can play with it a little bit more effectively. And like I said, you'll have a choice of doing a third exam or doing a modest project like this. Okay, and once you'll see the description of the project, I'm going to wait until we come back from Thanksgiving for that. Once you see the description of that, you'll be able to make up your own mind of which way you want to go with that. But correlation and regression is important topics, so Don't go away. Don't come back. Come back after Thanksgiving. Don't disappear. We need to cover that material as well. You'll be reading a lot of studies, and you may be working with studies where you have to have an understanding of those topics as well. Okay, you guys have any questions? You haven't said much. I mean, it's not like you've looked like you're frightened or whatever, but I haven't had much feedback here today. You guys okay? Is there an area of this that you feel uncomfortable with? Is there one area? If you had to pick one, I'm going to be a little bit more assertive. Which of all the things we covered, from confidence intervals all the way up to chi-square and odds ratio, which of these analysis of variance, the t-test, equal variances, unequal variance, which of those do you feel the least comfortable with? Pick one. What do you think? Like, do you like Macintosh apples? Do you like, when you go to the store, you got to pick, they got 88, when I was a kid, they had like 2 different kinds of apples. Now they got 8,000 apples, right, from everywhere in the world. And you got to, when you go into the grocery store, you got to pick out an apple, right? So this is an apple. Give me an apple. Which apple are you going to pick? I mean, I tell you the truth, I've had an occasion, I've gone to the grocery store, looked at all those apples, couldn't make my mind up, and didn't buy any apples. But hopefully, in this case, I'll force you to buy an apple. What do you think? Don't look at her. She's got her own answer. Oh, you mean the post-hoc test? Oh, the post-hoc test. Okay, analysis of variance. Okay, good. I will make sure to cover that again when I do a review, when I do a question and answer session. Okay, so that's analysis of variance. That's a post-hoc test, where we first do the analysis of variance to say that we can go ahead then and go on and do where we're comparing means of more than 2 groups, right? And then once we've established that at least 2 of the groups have different means, we have to go back and do those other tests to determine which of the 2 groups, which groups have different means and which don't have different means. Remember, on that one, it's not all or nothing. So in the beginning, it's you reject the null hypothesis if any of the means of those groups are different, right? But they don't all have to be different. So then you have to do those post hoc tests to determine which of the means are different. Okay. Do you agree with that analysis of variance or chi-square or? Okay, analysis of variance. Okay, no problem. Look at the videos on that, because the 4 videos that I did on that I think are pretty helpful. Especially maybe the one that we actually use SPSS to do the solution. Yeah, I mean, there's videos that are no more than 5 or 10 minutes long each. There's video showing me doing a solution using Excel, doing actual raw calculation for analysis of variance using Excel, and then another one using SPSS. Now that one I didn't bother doing a post hoc, because it was a lot more complicated. But I did repeat the same analysis in SPSS, where I got the same value and result for rejecting the null hypothesis. But in the SPSS version, I went on and did the post hoc test. So you can see both ways, how it's done manually, but then in SPSS, you can see it done on SPSS, but then take another step and do the post hoc test. Okay? Okay, good. I think my voice has had it today. Good. Okay, if guys online who've been virtually silent this whole time, have a good afternoon. And like I said, I'll keep your eye on Blackboard, and I'll set up a Q&A session for next week. Maybe I'll just come here and do it on Monday or something like that. Or do it remotely at the same time as the class instead. But the exam itself will be online. It'll be available from Tuesday on, from Monday on, excuse me. And you'll have at least a week to do it. At least a week to submit. Do 2 submissions if you want to. You don't have to do 2 submissions if you don't want to. If you got 100% on it, you don't have to do it another time, right? You got 98%, you said, that's good enough. Or even 95 or 90, even if you're not striving for too much, right? You're not forced to do it twice. If you don't want to, But if you will benefit from doing it twice, you have a second shot at it. You'll see which ones you got wrong, but not the answers themselves. Okay, just like the first test. Okay, take care, guys. Bye.